In this video, we're gonna try to find the domain of definition of these functions. So for each of these functions. So these are different functions, but their main topic is about the domain of definition of the logarithmic functions. So the first one is defined by the square root of the natural log of x. The second one is the natural log of 1 minus the absolute value of x. And the third one is the natural log of x over 1 minus the natural log of x. So we want to find the domain. Let's start with this first one. So our first function is defined by, let's call it f of x. So f of x is given by the square root of the natural log of x. Okay, and this question we can do it graphically first. Let's do it graphically first. So here we know the graph of the logarithm. Okay. So I'm looking for the values of x that would make this one positive, because here we need to have everything inside the square root to be positive. So that means everything should be above the x-axis. And from here, we see that it's 1 plus infinity. So it's the values of x. So starting from here, we're gonna have positive values. Okay. Here between 0 and 1, we have negative values. So here we see that the values that we get is between 1 and plus infinity. And this would make the domain. Let's check that one algebraically. So first, we need to have ln of x is bigger than 0 and x bigger than 0. So this first condition, what are the values when the natural log of x is bigger than 0? Okay? So the natural log of x is equal to 0 when x is 1. Okay? So that means x is bigger than or equal to 1 from this condition. And we can combine this first condition with this one. So we have the graph here. So when the line here, so this is 0, this is 1. So we want to have x is bigger than 0 and x is bigger than 1. So it's this double shaded area that would make this value true, this condition true. So we have 1 plus infinity as our domain of definition. Okay. So we graphically and algebra help us a lot. Next one is let's define this function. G of x is the natural log of 1 minus the absolute value of x. Here we need to pay attention to this condition here. So we need to find the values of x that would make 1 minus x, okay, bigger than 0. Okay, we can do this in many ways. Okay, let's do it both ways. Let's do it. This is the first way. So the first way is we add minus 1 to both sides. We get minus x is bigger than minus 1. And we multiply by a negative 1. We get x, the absolute value of x is less than 1. And what are the values of x that are less than 1? It's those values that are between minus 1 and 1 strictly. Okay. The second one is that we know how to graph the absolute value of x. So this is the graph, the absolute value of x. We want to see the values of x that are less than 1. So let me do it in a different color. So this is 1. Let's assume this is 1. So this is y is 1. So the values of x that are less strictly than 1, so 1, let's solve. When x is 1, we have y is 1. So when x is 1, the absolute value of 1 is 1. When x is minus 1, the absolute value of minus 1 is 1. So we don't want them to be equal. We want it to be less. So that means we need to get rid of the minus 1 and 1, because these are the value what they can which can help us reach the value y equals 1. So we want to get rid of them. Okay, so here when x is 1, we reach this value of y equals 1. When x is minus 1, we reach the value of 1. So we want to have x between minus 1 and 1 strictly. So this is graphically the result that we get, the same thing that we get using algebra. The next one, the third example is h of x is the natural log of x over 1 minus the natural log of x. So here we need to pay attention to. We don't want to divide by 0. So we don't want to divide the natural log by this one here. So the first thing to do is we don't want this one to be 0. So our first condition is 1 minus the natural log of x has to be different from 0. And also we need to have this one defined and this one defined. That means we need to have x bigger than 0. This condition gives us the natural log of x is different from 1. Okay? So this condition here, if you see, remember the graph of the log from the first example, so the natural log of 1 is 0. And this is 2, this is e, so this is e. And the natural log of e is 1. So this is 1 here. Okay, so we don't want to have that one. So when the natural log of something equals 1, of what value? Okay, which x give us the natural log equals to 1? So it's e. So you want to have x different from e. Okay, we can also use the definition of the log. So ln of x equals some y. It means that this is the base e, so that means e to some y equals x. Okay, and that means, and since we have this y equals 1, so that means x is, so here y is 1, so that means x is e. Okay, so we want x to be different from that. So we want x to be different from this one. That means x different from e. So here we have two conditions. We have x, this is our 0, and this is our e. So you want to have x bigger than 0, that means x in here, and different from e. So we're going to jump. So we have 0e union e plus infinity as our domain. So this is the domain for this function. Okay, and beside that, is there any value that would make this one different? Yes, you can work on something else, but for now this is the domain for our function. Okay, and we see that we need to combine. This is we can graph it by hand and see the domain, but algebra is helpful. So we imposed our two conditions, and from there we get our solution. We don't want to graph it because we can graph it, but it's a bit of work. Yes, it would take like 10 minutes to graph by hand. Yes, we can do it. You can add a +1. You can put minus here, minus sign, and add or 1, and add 1 and subtract 1, and do it. Okay, because we can reflect the natural log. We know how to deal with this one. Okay, we know how to graph this one. We know let's do it just quick. quick scale, but it's not gonna give us this one. It's a bit of work. So if you have this one, your natural log is this one, yes? So what's this one here? You flip it. Okay, what's 1? You shift it 1 unit. But this one is gonna be it's gonna be a bit of work. Yeah, so that's why we do algebra. We work with the algebra and we get our result. This is this is what we get.